Yeah, I'm going to be talking to you about some work I've done trying to use Bayesian deep ensembles to model the flux of the radiation belt's outer boundary. Let's see. So, what are the radiation belts? What is the outer boundary? Why do we care? Essentially, so we've got the radiation belts, which are these sort of red regions here that we can see about the Earth, which compose of magnetically confined charged particles. We've got the inner belt here, which is mostly protons, and we've got the outer belt, which is mostly electrons. My work focuses on this outer belt. One of the things you can see in this plot is that we have things like GPS satellites and geosynchronous orbits, which exist close to and within the outer radiation belt. Given the energies of the electrons in the outer belt, it can be damaging to spacecraft, both on a long-term basis in terms of just degradation of instruments and stuff, but also on a short-term basis, if you have a storm and there's a sudden enhancement and you have very high energy electrons, they can penetrate into spacecraft and destroy circuitry and things like that. So being able to model this system and predict the sort of long-term effects, but also the short-term effects, is really important to the continued lifetime of spacecraft operating in this region. So as I said, most of the way we do this is through modeling. And one of the really important parts about modeling the outer radiation belt in physics-based models is the outer boundary condition. This is like a twofold thing. It's both the location, but also the flux through the boundary. The reason it's the flux is essentially this boundary condition acts as a source for the simulations. So it's a source of particles or energy. And so it's really important to be able to characterize it properly. However, what lots of models do is construct a boundary condition where we have lots of data. And unfortunately, where we have lots of data doesn't necessarily coincide with where the actual outer boundary is. So what we're doing in this project is essentially building on some previous work to identify where the outer boundary might be located. And now we're going to try and model the fluxes at that boundary location so that people who do radiation belt modeling can use that as inputs to their models. So yeah, as I said, the goal here is to essentially take data that we have of electron fluxes. So in our case, that's GOES data, which is in geosynchronous orbit, and map those fluxes to the boundary location, which we take data from using Themis, like Jacob described there, which crosses through this boundary over time. And on top of just doing this mapping, we're going to parameterize it either by solar wind variables or geomagnetic indices. And we're going to train our neural networks to essentially try and map between these data and tell us what the boundary is doing in a sort of real-time basis. So one of the additional things that we're kind of trying to do here is trying to do it probabilistically. So rather than just having our neural network output a single value, we want it to give us a distribution. This is useful because one, a distribution just has more information. It's not just a point value sample from that distribution, it gives you more information. In terms of its use in radiation belt models, there are at least a couple of data assimilation models of the outer radiation belts. And having any information about the kind of distributions for these things helps with the downstream data assimilation. And I guess on top of that, it also indicates the confidence that the model has in its own output. And I'll talk a bit more about that in a second. So we have sort of two aspects of how we get probabilities out of this. So one of them is just kind of using what I'm calling Bayesian neural networks, probabilistic neural networks. And in this case, what we're doing is instead of outputting just a prediction of, say, the flux that we're interested in, we're going to predict a value of the flux and a variance. And from that, we can construct a Gaussian distribution. So essentially, we're predicting a Gaussian distribution at each point. And by using the negative log likelihood as our loss function, we're essentially optimizing the fit of these Gaussian distributions to the data. That gives us some idea about the irreducible uncertainty. And then because we also want to capture the reducible uncertainty, we use an ensemble of these trained neural networks. And so to introduce some like randomness in that, we have bootstrap training data. So we train each of our models on slightly different data. This is after optimization. We initialize the weights randomly, and the optimization procedure of the weights is also stochastic. So there's lots of sort of perturbations in each of the individual models. And basically by using an ensemble in this way, we're sampling from the posterior distribution over the weights, which gives us some idea of the variability that arises during training, and specifying the weights. So the variance that we're predicting with our neural network, that tells us about the reducible error, and that comes from a couple of different sources. The one that most people will be familiar with is sort of measurement uncertainty. That's quite an easy one to think of, but it's also, say, the inputs to your model maybe don't or can't fully capture the state that you're trying to model. So you're inherently going to have noise that you're never able to capture. But also your model architecture might not be perfect. Neural networks are universal function approximators, but they are approximators, and so there are inherent limitations in that. As a little example of what sort of this uncertainty looks like, if we have some variable x that we're using to predict target y, we might predict sort of this solid line which passes through the data. But we can see that the data points are distributed quite noisily about this. And so whilst it gives us a deterministic value, say from a prediction, we also want to know what the spread is here, because that really tells us more about the system we're trying to model and the variability that it has. So that's what the variance tells us in our probabilistic neural network. But you can see that there are these regions where we don't have data, where the variance goes right down. And that's not what we want. We don't want our neural network to think that it's very well constrained in its predictions when we don't actually know what the true value should be, because we don't sample any data in these regions. So this is where the ensemble comes in. And by using an ensemble and perturbing each of the members, we essentially approximate the uncertainty that we're getting in these places, which is sort of out of sample. So it allows us to get a more realistic understanding of the uncertainties for predictions where we don't have much data. So with that kind of background, what am I actually doing? So for inputs, I take the GOES data that I mentioned, and this is 2 measurements of integral flux, as well as some standard deviations and some spacecraft ID. That kind of coincides with what Jacob was saying about intercalibration. I found that including the spacecraft ID did help with prediction, which suggests there might be some intercalibration issues between the older and newer ones. We also want spatial information because we don't necessarily expect the mapping from the GOES flux to the outer boundary to be consistent in terms of where the spacecraft are located. So we have the position of the GOES spacecraft and the position of the Themis spacecraft so that we can learn these spatial dependencies. And then we're making 2 separate models. I'll mostly be talking about just one of them because the results are quite similar. But we have an index model, which uses auroral indices, and then some of these kind of more ring current-y indices. These are all from the Omni dataset. And then for the solar wind, we have the interplanetary magnetic field, the solar wind speed, density, temperature, pressure. And all of this is on minute resolution data. And then what we're trying to predict here is not just a single value of the flux and an associated variance, but actually in a single model trying to predict the 11 energy channels and the 11 values of flux that Themis measures at any given time. So we've got kind of a bit of a schematic here of the training procedure, and this is what our model looks like. It's quite a complicated one. We have essentially 4 hidden layers and then 11 sub-models, which we're using to sort of tailor the model's predictions to any other nonlinearities that occur at different energy channels, essentially. And then our outputs, we have 11 means, 11 values of the flux, and 11 variances. And all of this is trying to predict the flux that Themis measures at about 8.25 RE, which we found in a previous study to be roughly the quiet time location of the outer boundary. And generally, we find that the model does pretty well. In terms of radiation belt stuff, it's worth considering that we're in a very dynamic system. So like the values of the flux can vary by 4 orders of magnitude in quite short amounts of time. And so typically people talk about predictions for radiation belts in terms of orders of magnitude. We get to within a factor of 4 on a statistical level. We have some plots here sort of talking to these results. So the top row here is for 3 of the energy channels that we're looking at. We plot the true flux on the y-axis and the predicted flux on the x-axis. And you can see there are some white lines on these plots, and those correspond to what would be a perfect prediction. Obviously, we're not quite at a perfect prediction here, but the dashed lines show a factor of 5 error in the prediction. And we can see that almost all of the time we're within a factor of 5, which is good. And we can see that we get worse at the higher energy channels, but that's not wholly unexpected given that this is significantly more variable. There's 4 orders of magnitude here compared to only 2 orders of magnitude for the lowest energy channels. If we want to look sort of more specifically at how the predictions differ, we can plot the residuals. And from these, you can see the distribution, and the box plots here sort of summarize that. And we can see that the median predictions are very close to 0. So the median is that we're predicting correctly. There's a slight bias towards over-predicting. So these more negative values mean that we're predicting the flux a bit too high. But we can see that the interquartile ranges for these distributions are well within the factor of 5 that's represented by these dotted lines. So we're pretty pleased with that. And then to summarize how the performance goes across all of the energy channels, we can see that for the very lowest ones, we have pretty low RMSEs. These correspond to, I think, a factor of 2.5 error. And we can see that this gets worse with increasing energy channels. And up here, we're at about a factor of 4. So that kind of summarizes what we saw over here. This is the mean absolute percentage error, which shows fundamentally similar results. But then in contrast to that, if we look at the correlations between our predictions and the true values, we see that for increasing energy channels, we actually get better. And this kind of speaks to the fact that the higher energy channels might be more strongly driven. And so it's easier for the model to pick up the sort of time, the time dependencies of how it changes with response to the input parameters. These results are all for the index model, but the solar wind model is pretty much identical to this, so I'm not showing both of them. But overall, we're quite happy with how this has turned out. So just as a quick summary, and then we can hopefully talk more about it if you have specific questions. What we wanted to do here is to characterize the flux distribution at the outer boundary so that it could be usefully incorporated into physics-based models as a more appropriate boundary condition. We're doing it to a different location where there's much less spacecraft data. So a model like this is immensely useful because just using Themis data, we couldn't reconstruct this real time because Themis doesn't sample this boundary location very much. So we need a model of it to really characterize it properly. And we provide probabilities based on all of this, which is hopefully useful to data assimilative methods and just provides more information. So we did this. We've got 2 neural networks. We parameterized the GOES fluxes, which is sort of what is typically used for boundary conditions, and then either the solar wind or geomagnetic indices. And we use that to parameterize the flux that we see at our boundary. And generally, we find that both our models perform pretty well. We're quite happy with how they perform. And yeah, like I said, the correlations, we're seeing that it's easier for the model to seemingly pick up what is more obvious physics in this sort of domain. Yeah, thanks.